No big deal. All right, so I'll have to use my pointer. My R1 there means one-dimensional space. So just a straight line. There's nothing else exists, just a straight line. And so if we write x equals 0.35, that means that on a number line, we go 0.35. If you grab this, you can move it around. Wow, that's real fancy, whatever, okay? There you go. Change your x value, one-dimensional space. Then there's two-dimensional space. As soon as you get to two-dimensional space, you have the concept of an x-axis and a y-axis, right? So normally we orient the x-axis out to the right, your y-axis up, right? So to the right is positive x, positive y is up. I'm going to put this, I put this board over here so I could put anything else that I wanted to down here. In R2, we have x, and I'm going to put plus here and y plus there, just to remind you, right? That's what it is. Could have done it here too. In fact, I think I will. This may seem very trivial right now, just bear with me. X, y, plus, plus. Okay, now, of course, if we change the x coordinate, that moves us left and right. We change the y coordinate up and down, right? No one's blown away, I hope. But when we're sitting here in two-dimensional space, right? When we're in 2D, if we write down in two-dimensional space, if we write x equals 3 in R2, it is not a point, right? In R1, it is. In R1, it was the point 3 on the x-axis because there was no y-axis. But in R2, when we write x equals 3, we no longer have a point. What do we have? A vertical line. It's every point with an x value of 3. Well, I can't go out to 3, but here we go. See, that's the equation. X equals 1.25. That's what you get geometrically. You get a vertical line. So, I mean, that's one of those little subtle things. If you say x is 3, plot it. Well, in 1D, it's a point. In 2D, it's a vertical line. In 3D, well, we're going to talk about that, right? So every point, notice that if I pick any point on this line, what's the x value? 1.25, right? Any point. The y value can be anything. So we say the y value is free. Y is free to be what it wants. We call it a free variable. It's just free to be any real number. Now we could do it the other way in R2, and instead of saying x is a number, we can say y is a number. So what are we going to get if we do y as a number? We'll get a horizontal line instead. Hey, who are you? Daniel? I thought I already counted you. Daniel? Oh, yeah, you're the first one. Okay, hold on. I got this for you. This, and this. Okay. All right. So we have whenever we're in R2, y equals a constant. Our x is free. That you see how it says it up there? Yes. All right. Now, there's some other important lines in R2 that we're all familiar with. Y equals x, that's the identity, right? Whatever your x is, your y is. All those points that satisfy that equation is this line. Here's 3x. Here's an example of a line with a negative slope to it, right? So we should be familiar with all of these. Now we talk about R3. Okay, so now we're going to move into three-dimensional space. So I want you to first look at this here, and what we have is is almost like R2, isn't it? I mean, that's R2. Our x is positive to the right. Our y is positive up and down. So if I move this point, x value left and right, my y value up and down. But now we have a third coordinate, which is the z value, which gives us our third dimension. So where is the z? coming out of the page, right? It's coming out of the page. Now, if you go and you grab your mouse at home and do this, you just click it and just move it. You'll see, well, that didn't work out too good. I'm off the screen. If I just click normal, there we go. Give me a second. There we go. Okay, that's good. So X is coming out here, Y is coming out here, and Z is going straight up and down. So I'm going to write that on my notes page here for R3. The best way to draw R3, in my opinion, there's two ways. You start with a kind of a flattened out X, like this. Kind of flatten it out, though. Don't draw true, perpendicular lines there. And then come straight down. Your X positive is here. Your Y positive is here. And Z positive is straight up. That's one way to do it. I'll kind of switch in class. But does everyone see that the X, Y is like the ground? Okay, if I come in here and kind of imagine shading this in like this a little bit, like that's a piece of paper that we've always had, but now we have the Z popping out of it. Do y'all see it? Okay, that's one way to do it. Another way to do it that I've seen is where you go like this, and you can extend this out this way. This is X positive, this is Y positive, and Z positive. Either way. That make sense? Okay, nay? I don't care which one you use. Now let's look at some things here. If I take my X value and move it, it's going to move along the X-axis, see it, right? Take it and move the Y positive, I'm going to come out some Y, right? And then if I make my Z positive, I should go up. So the blue represents the value of Z, the green is Y, and the red is X. Do y'all see it? You can label them if you want, the X, Y, and Z. Now, what does an equation in R2 look like now? So if I write down, let's say, X is 5 here. A plane. That means that X has to be 5, but your Y value can be anything you want, and your Z value can be anything you want. So let me show you this. I'm going to try and move this to 5. If you can't move it to 5, just so you know, people who do download the player, there's a little plus symbol here. You can come in here and you can actually change the value. There we go. So do you see the plane? Maybe not. So maybe you need to spin it to the side a little bit to see it. Okay? So if you go out the X-axis, 5 units, and imagine every point that's moved out 5 units, and every Y and every Z up and down, left and right forever, you get a plane. So that's what X equals 5 looks like. What does Y equals 5? Oh, well, you know what? I should say this before I move on. We call this, if X is 0, okay, if X is 0, then your plane actually hits which axis is this? The Y-axis, and then which axis is this? The Z-axis, right? Your plane actually passes through the entire X-axis and the Z-axis, so we call it the XZ plane. It's called the XZ plane. Or, I'm sorry, I said Y. It was Y. Y-axis and Z, right? Then I switched to X. Y-axis and Z, so we call it the YZ plane. My apologies. Do y'all see that? So if we now change the X value, move it out 5, what we get is a plane that is parallel to the YZ axis. The YZ axis, move a plane off of it, they're parallel, right? 2 sheets, they don't intersect each other. So let's switch it now. Let's go and let's fix a Y value I'm going to take those labels off. Let's fix a y value and let the x and the z be free, and what will we have? Another plane, right? But this one is parallel to which plane? The one that passes through which two axes? The x and the z. So that would be a plane parallel to the xz plane. With me? And then, of course, if we fix the z value, we're going to have a plane that's parallel to what? This plane would be parallel to which plane? The y-axis or the xy plane. So there's really like three major planes, reference planes in three-dimensional space. There's the yz plane, right? There's the xz plane, and there's the xy plane. These planes are all parallel to those. So I guess in summary of what I've said so far is that if we have someone writes down x equals 5 and asks you to describe what it is geometrically, right? Your next question should be, what space am I in, right? Because you can't show me x equals 5 or plot it unless you know what dimensional space you're working with. In R1, we said that's a point. In R2, what is it? A line, right? In R3, this would be a plane. And then in R4, well, then we start losing a visualization. But you can talk about R4, R5, R6. We'll stick to R3 here, okay, for now. Any questions on that? All right, now one of the most important things with this is what's called the right-hand rule. This did not get printed, I believe, right? It's not in there. That's why I put 10.1.5b. Have y'all noticed that my notes go in that order? Sorry. Chapter 10, Section 1, we're on Note 5b. The next note will be 10.1.6, and that's the way I number things throughout the whole semester. I try to do that so that if you ever need to like call up one of your classmates or even me, and you have a question about something that's easy to reference, you can just go, hey, I don't understand 10.1.7, what's going on there? So the right-hand rule is something that, it's a rule that we all agree to. It's the standard in which we draw our three-dimensional space. And you start by getting your right hand. And the rule is this. Your fingers should point in the positive x direction. So you see these fingers are kind of in positive x direction. When you curl your fingers, it should curl towards the positive y direction. And your thumb should point in the positive z direction. That's the right-hand rule. Positive x curls to positive y, and positive z straight up. So let me give you an example. I'm going to draw something here, and you tell me if this follows the right-hand rule or not. So how about this? Does that follow the right-hand rule or not? If your fingers are pointed out to positive x and you curl towards positive y, your thumb needs to point to positive z. So I didn't put positive z on here, did I? Here's positive z down here, right? So what if I do this? My hand's here. I curl from positive x towards positive y, and my thumb is pointing towards positive z. So that does follow the right-hand rule. Can you all see it or not? This is where drawing on a sheet of paper is hard, because it's hard to see the 3D. Now look at if I use my left hand, which I'm not allowed to, I curl positive x, right, towards positive y. My thumb is pointed negative z, but I'm not supposed to use my left hand. I'm supposed to use my right hand. So the only way to curl from positive x to positive y is to do this, right? And then my thumb is pointed down towards the positive z. So the answer is yes, that follows the right-hand rule. And of course, that one, no, that wouldn't work. Positive x curls towards positive y. My thumb is not pointed to positive z, so that doesn't follow. So every time you draw something in three-dimensional space, your axes must follow the right-hand rule. If they don't, then the math doesn't work, because we all have to have a convention that we agree upon. That's the convention, right-hand rule. All right. How far into this do I want to get? I don't know. Let me ask you this. Is it okay in two-dimensional space to draw your axes like that? Or do you have to follow some rule in two-dimensional space? It doesn't matter in 2D, and here's why. And I could do it with a sheet of paper. Let me do this one. Okay, this is what I drew up here, right? Positive x, positive y. We are used to seeing this. Right? That's what we want to see. That's what everyone's happy with. Here's what I drew. If you just flip the page over like this and look at it from the other side, you do have positive x and positive y. This is the convention, yes. But I could do all the math I wanted in the same drawing, and all the math would be okay. It would be the same as this. All right? In 3D, you can't do that. In 3D, I cannot. It just turns out that if I draw this one, right, which was wrong, this doesn't follow right-hand rule, there's no way to like go to the other side or look at it a different way where it does follow the right-hand rule. You can't do it. So in 2D, it doesn't matter. In 1D, it doesn't matter. In 3D, you have to start to have a convention that we all agree upon. All right, next one. Okay, just like in pre-cal, you learned in pre-cal about quadrants, right? Remember quadrants? Two-dimensional space, angles. You had Q1, Q2, Q3, Q4, right? And why were they numbered backwards like that? And I mean, why wasn't the top left 1 and then 2 and 3, 4? I mean, why did they do that? Just to mess us up, right? Yeah, it was all based on angles, and you always said you started out with angle of 0 is the x-axis in the positive direction, right? And then positive angles would start to grow from that, right? So your angles would go this way. And so it's natural, if you do it this way, that as your angle grows, you start in quadrant 1, then you get to quadrant 2, then you get to quadrant 3, and you come back around to 4. If you did it 1, 2, 3, 4, it just wouldn't work. I mean, it just wouldn't make sense that way. So there's our quadrants, right? We have 4 quadrants in two-dimensional space. In three-dimensional space, what you have are what? Well, I kind of give it away here. Octants, right? Oct meaning 8. So remember in two-dimensional space what we had. I'll put it over here. I don't feel like switching back and forth. If you were in quadrant 1, your x was positive and your y was positive, wasn't it? If you're in quadrant 2, your x was negative, your y was positive, and then you could do the rest, right? For octants, what I want to do is talk about, first of all, what would I get if I had all x's, all y's, and all z's positive? Where would I be? And that's your first octant. So what you can do is you can grab this slider, octant 1, you can slide it, and you can see that square is taking up the first octant. And of course, it goes out forever, right, in each direction. And if you click up here on click info, it tells you x positive, y positive, z positive. Now I'll go to octant 2. Octant 2 is basically, well, did you see that octant 1 was quadrant 1 and everything above it? So octant 2 is quadrant 2 and everything above it. So there's your quadrant 2 over there. And the information there, you tell me. What is it? What's required to be in quadrant 2? I mean octant 2. X negative, Y positive, Z positive. And then octant 3, what's the requirement to be over there in octant 3? X negative, Y negative, Z positive. Octant 4, positive X, negative Y, positive Z. What about octant 5? Where do you think octant 5 lives? Below octant 1. So you would have X positive, Y positive, Z negative. Uh-oh. I may not go to octant 5. Oh, there it goes. Yes. Let me take some of this stuff off. You want me to rotate it? How do you want to see it? Like that? Sorry, it's twisting. If it twists, you have to come up here and there's a different, see, my cursor changed. There we go. It gets some. Is that okay? All right, now I don't know if I'm going to be able to spin this thing back around. Come on. There we go. There we go. All right, so now octant 5 is everything below octant 1, right? And then I can keep going around. Octant 6 is below octant 2, and then so on and so forth. So I'll let you mess with this on your own. All right, you get the idea? 8 octants. Octant 5 is below octant 1. So look, I'll take, yeah, the only difference is Z is negative. So let me take all the octants out except 1 and 5. So remember, the ground is the XY plane. Octant 1 is that ground and everything above it, and then octant 5 is everything below it. Can I move on, or are we all right? Okay. Now, some examples of surfaces. A surface in R3, we've already talked about this, planes, right? Planes. So the first plane that I have here is X equals a number. And if you grab this, you can move it back and forth, okay? You can see your planes moving along the X-axis. It's parallel. That plane is parallel to what? The YZ plane. Good. All right, now let me get it out of here. All right, now how about Y? What about Y equals a constant? I'll get that one. That's parallel to the XZ axis. And then if Z is a constant, we said that that plane was parallel to the XY axis. Those are all examples of surfaces, but they're very simple surfaces. They're planes. Planes are like the most simple surface we have. That's equivalent to, a plane is almost equivalent to like a point in one-dimensional space. It's almost the most basic geometric representation you can have. It's just X is a number, or Y is a number, or Z is a number. All right, now we start getting into some stuff. We know from, I don't know, college algebra maybe, or who knows where it was. We recall that whenever you were in 2D, right, X and Y, that if you wanted to find the distance between 2 points, x1, y1, x2, y2, that you could construct a right triangle, drop your perpendicular there, And then you know that this side, the side here parallel to the x-axis, would be your x2 minus x1. Your side that's parallel to the y-axis there would be y2 minus y1. And if we call this d the distance, then by the Pythagorean identity, we get a squared plus b squared is c squared. So we get this side squared plus this side squared is this side squared. Then we take the square root on both sides, and that gives us the formula d equals square root x2 minus x1 squared plus y2 minus y1 squared, right? That's what we had in 2D. The question is now, what if we have 2 points in three-dimensional space? What is the distance between them? Understand? So in this, first I give you the formula, x, y, and z. Okay, that's 1 point. I give you an x, I give you a y, I give you a z. So instead of saying x1, y1 like I did a second ago, I'm just saying x, y, z. Your second point is RST, some other point. The distance between them is d equals square root x minus r squared plus y minus s squared plus z minus t squared. So it's the difference of the x coordinate squared plus the difference of the y coordinate squared plus the difference of the z coordinate squared, square root. Your first bonus problem of the semester is to prove the formula to be turned in next class. All right, and try and put as much geometric backing to your proof if you want. So you'll turn in, put bonus on it, and put the date when it's due, 1/27/14. It's just basically derive the formula. I kind of already give you a hint in my drawing, because the blue is the distance we're looking for, right? The distance between these 2 points. Can you all see that in 3D? Do you all see those 2 points? If you can come up with the red sides, then you've got Pythagorean identity, right? So you need the length of that side, and you need the length of that side. But it's not trivial. You have to work for it a little bit. It's not simple. You have to work a little bit to get those. So if you can prove that, that's fine. If not, we're just going to take the formula, all right? And you can move things around. It's not very exciting. I'm moving on. Would you like to do an example, or we'll do them at the end? Let's do them at the end, all right? I've got a couple of examples. Right now I'm just kind of filling you with a bunch of stuff. Okay, we get to our next type of geometric object in three-dimensional space, and that's the sphere. Please recall from, I don't know, pre-cal, college algebra, calculus 1 and 2. What's the equation of a circle in two-dimensional space? In R2, a circle centered at HK with radius R. Anyone remember the general equation for a circle centered at HK, radius R? Close, you're missing something. H and K are fixed numbers. That's the center of the circle. So like, for example, if I go here and I say, look, here's a circle, the center of that is 2, 3, and let me say the radius of that is 2. What's the equation of that circle? That's the question. X minus h squared plus y minus k squared equals r squared. Good. So it's in there in the cracks maybe of the short-term memory, but here's the general formula. X minus h squared plus y minus k squared equals r squared. That would be the equation of that circle. And this particular circle that I drew here, the equation would be x minus 2 squared plus y minus 3 squared equals what? R squared, so 4. And if I wanted to, just to have fun, I could actually expand those out, right? If I felt like just enjoying myself here a little bit, I could multiply. What's that? Oh, plus 4. Thank you. Right, I could do that, and then I could start combining some things together. I'd have x squared minus 4x plus y squared minus 6y, and then let's get our constants together there. 13, take it to the other side, right? So minus 9. Or I could leave it on the left side as plus 9. It really wouldn't matter. So this right here is the equation of a circle, centered at 2, 3, radius 4. My question to you is, can you go from here to there? If I gave you this, bottom line, could you recover the equation? And then if you could recover the equation, you would know the center and the radius, wouldn't you? How would you get there? Complete the square. You would have to complete the square on the first two terms. So you would have to take these two terms here, right? Forget anything else exists and complete the square. So to complete the square, you take the number in front of x, which is negative 4, right? Take half of it, which is negative 2. Square it, which is 4. You add and subtract 4. So you would basically have this. You'd have x squared minus 4x. And then next to that, you would add 4, subtract 4. Then you do the exact same thing for the y squared minus 6y. You would take half of negative 6, which is negative 3. You'd square it, which is 9, and then add and subtract 9. So you would get this, plus y squared minus 6y. What did I say, plus 9 minus 9? But then what do I still have there? What did I still have? That plus 9, right? So I would have had to account for that, plus 9, and then I have equals 0. Now when you complete the square, if you remember this, the first three, these terms right here, should factor. Right? You should be able to factor that, and then these three should factor. What do those first three factor to be? What's x squared minus 4x plus 4? X minus 2 squared. What is the y minus 6y plus 9? Y minus 3 squared. And then we have all these constants. Negative 4, negative 9, positive 9. That leaves me with what? A minus 4, right? I have a plus here. I have a minus 4. I'm taking it to the other side. And I get 4, don't I? And that is the general equation of a circle. You see? I just wanted you to see in R2, you should be able to give you a center and a radius, you should be able to come up with the equation. Or if I give you the equation all messy, you should be able to complete the square and go back to the general form. Questions? You got a question? Yeah, it's the number in front of the x, half of it, square it, then add and subtract it. So where I added and subtracted is right here. So I took the negative 4, divided it by 2, and squared. You always do that for completing the square. All right. Now, that's in R2. In R3, we don't have a circle. We have a sphere now. We're going to talk about a sphere. So look at the formula for the sphere. It's very similar to the circle formula, isn't it? We have x minus h squared, same thing, plus y minus k squared, same thing. But now we have an additional plus z minus l squared equals the r squared. So all that's been added is that plus z minus l squared. The L is the z coordinate of the center of our sphere. So our center is HKL and our radius is r. So I have here a sphere. You can control the center by moving the x coordinate, or the h moves it on the x-axis. The k controls it on the y, and then the L controls it up and down, and then you can control the radius of it if you want. Well, I have negative radius. That doesn't make sense. Okay? Questions? What you're going to be asked to do in your homework is you're going to be given an equation that's going to look a lot like this one right here. But you're on top of having like the x squared minus 4x and the y squared minus blah, 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 you're going to have, guess what? Z squared minus z something z, and you're going to have to complete the square on all three and then recover the center of your circle and the radius that way. But it's the same exact sort of format that I did on this. Questions? Yes. 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 Good question. It's always the positive. Here, I don't want to go too far on this, but I think it's important because I don't know how this happens, but especially as a Cal 3 student, if you have something like x squared minus 4x and let's say plus 1, and I want to complete the square, you know, I take half of this number, negative 4, and then square it so I get 4, right? What I do is I write x squared minus 4x. I add and subtract 4. And yes, the added one is always the one that will group with these first three, or those first three will group, and then the plus one's hanging out the end. The reason I'm bringing this up is because a lot of people learn completing the square, and what they remember is that you take half this number, you square it, so I got 4, and then they're taught add it to both sides, right? Put a 4 on both sides. Well, here's the problem with that. What if you're dealing with an expression and not an equation? If you have an expression, not an equation, you don't have another side. So you can't add 4 to both sides. Perfect example is something like an integral where you have like square root x squared minus 4x plus 1. If I have to complete the square in there, I don't have an equation to work with. If I think that the only way I can do it is by adding 4 to both sides. But by adding and subtracting 4, you don't need an equation. So this is way more powerful. And so you could do that, and then that looks like a formula, and you could finish it off. I don't know. I just wanted to touch on that a little bit. If you have feel like you have any like loose ends that need to be tied up on completing the square, please feel free to get with me on that. You know, I didn't mention this, my office hours. I think this is important. I go through it in the orientation video, but I'm in my office before this class for 2 hours. So hopefully you don't have a class right before this, but from 11 to 1, I'm just sitting there waiting for students to come in. And then after this class, I'm there for an hour. And longer if needed, but on paper, it's from 3 to 4. Okay? And then on Tuesday, Thursday, I'm also in my office, and on Friday. I would encourage you to come to me for help instead of trying to go to the tutoring lab or something. You might wind up confused that way. JH111A gets you to the door, and then just ask them or just walk in there and look for my name on the office. Because this class wasn't initially going to be offered. We usually offer only 2 Cal 3s, and I requested a third one be put in, and this was the only available room we had. Yeah, I actually like it. It's kind of different. It's cold. I told them to turn it down. Or turn it up. I just told them to turn it up. Because it was 65 when I walked in. I was saying I was cold and everyone else saying they're hot, so I don't know. I don't know what's happening. Okay, here's the coconut problem. Okay, here's the coconut problem. We have a coconut. It's a sphere, right? It's a sphere but it's not, well, a sphere we look at it as like a shell, right? The sphere is just the surface. A ball would be solid throughout, wouldn't it? A coconut is kind of like a ball that has the inside of it taken out. So I kind of did this so you can pull it back and you can just rotate to just kind of see, you know, if you cut it, that's what we're talking about. It's been cut. So my question to you is, how would you represent a coconut? Let's say the outer radius is 4 and the inner radius is 3. How would you be able to tell me or represent that geometric object to me in mathematical symbols. So let me write it down on a different page. What we have is a coconut, right? We have coconut. Now here's my ill attempt at 3D rendering here by hand. So there's my ball, and inside of it I have cut out a smaller ball. And see, it just starts to get to be a real big mess, right? It's hard to see. What I'm going to tell you is that for the outer one, the radius is 4, and then for the inner one, I'm going to say that the radius is 3. So how could you tell me or represent all the outside of this coconut, all the material inside until you get to that empty void in the middle? Oh, you could do an integral. Oh, yeah, you could. Yeah, that would be a little ugly, though. I mean, yes, I agree. That would be like a volume, though. I'm talking about, like, if you wanted to talk about a circle, you could do, like, use the formula x minus h squared plus y minus k squared equals r squared. That's your formula for a circle. For a sphere, a fixed sphere, we know the equation, right? X minus h squared plus y minus k squared plus z minus l squared equals r squared. But how do we represent not a sphere, but some stuff inside of it? So we want the radius to start at 4, right? And we want it to go down until the radius gets to what? 3. So watch the way I do this. First of all, where's this coconut centered? Let's assume the origin, okay? So I'm going to throw the origin in here right into the middle, like this. The way I could represent that is x squared plus y squared plus z squared. That is the formula for a sphere replacing h, k, and l with what? 0, 0, 0, right? So just imagine that's x minus 0 squared plus y minus 0 squared plus z minus 0 squared. Now if I put this, and don't write this down, if I put this, is that the coconut? No. That's only the outside of the coconut. If I put 3, that's only the inside of the coconut, right? So don't I want my x, y, and z's to satisfy this? I need them to be less than or equal to 4. What's our radius? Oh, our radius is 16, right? Radius squared, thank you. That'll be r squared. That's 4 squared. And then less than or equal to what? I mean, greater than or equal to what? 9. What this does is that gives me every point, right? Every point that x, y, and z that satisfy the fact that the radius squared is less than or equal to 16. That gives me the outside of the coconut and then everything inside. Kind of makes sense? It's an inequality. What I'll do after this is I'll show you something a little different. Watch. What if I wanted to do a circle in two-dimensional space, radius is 4, and I want everything inside of it? So we know r squared is 16, so this would be, I need my x squared plus y squared to be less than or equal to 16. So let's just pick some points on here. What about this point? Does that point satisfy that inequality? What's that point? 4, 0? If you plug in 4 for x and 0 for y, does it satisfy that inequality? Yes. Okay, what if I don't do that? What if I pick this point here, 2, 0? Does that satisfy it? Yes, 2 squared plus, so that works. What if I pick the origin? 0, that works. 0, 0. And if I pick something like here, right, that should work also. Anything here? Anything? Because look, the points that live on the edge of the circle are x squared plus y squared equals what? The ones on the edge. X squared plus y squared equals 16. So x squared plus y squared less than that is everything inside that circle. It's every radius smaller than the 4, all the way down to 0. Hey, what's up? What happened? What happened? I don't think so. What does it say? Sound or no?
No, just a projector problem.
We're good.
All right.
We're good. Thank you, though. No, it's all right. So does this one make a little more sense then now? What we're saying is all the points that are less than the radius squared, but then for the 4, right, which would be the outside of the coconut, and then the inside would be a radius 3, which would be 9. So let's again pick a point here. What about this outside edge? That is the point 3, 0, 0, isn't it? Out 3 on, well, I have my, you know what, that's wrong. That's 0, 3, 4. I'm on the y-axis, sorry. This is x, this is y, this is z. So that would satisfy it, right? 0, 4 squared, 0 squared. So that'd be 16. That lives within that interval. Now, if I pick the one on the inside of the coconut, that would give me 0, 3, 0. And that would also satisfy this, wouldn't it? Now, what if I try and do the origin? Wouldn't work. 0, 0, 0 doesn't satisfy that inequality. So the inequality gives us the I guess, the solid. It creates the solid. Instead of just a shell of a sphere, gives us the solid going in. So we can work with inequalities and mess around with them pretty good. Questions on that? Okay, let me challenge you with another one. What would this look like? In R3, what would that look like? Z bigger than or equal to 1. What would it be? Can you all visualize? It's infinite, yeah. What's Z equals 1? What does Z equal 1? It's a plane that's parallel to the floor, the XY plane, right? Moved up 1. This says your Z can be 1 or anything bigger than 1. So it's that plane and every plane stacked on top of it. So it's like this infinite solid that's 1 unit high. So if like this is the ground, 1 unit high from here up, straight up is all solid. And every, to the left, to the right, up. Okay, it's just not below 1. Make sense? What would this look like? This and x squared plus y squared plus z squared less than or equal to 9. Sphere with radius 3. But these are, now I'm asking you to do them both together. That one and that one. So that's sphere radius 3. But your z also has to be bigger than 1. So what you're doing is you're coming up off the ground and you're cutting the bottom part off the sphere, right? So it's going to look like this. Like if we move up 1, it's going to be like this. 1 unit off the ground. It'll be just the top of this sphere. And is it solid? Yes, because the inequality here meant that it was that outer shell and everything in. So it was a ball, wasn't it? A ball 3, ball radius 3. And we came in and say, but you got to cut off everything from 1, like down below 1, cut it all off. So you just got like this cap. It's 3-dimensional cap. Solid. You all see that? Okay. Let's get back to the notes. Oh, wait, we're done with 10.1. Let me tell you a little bit about the homework you should do from 10.1. I'm gonna share something with you here that's really important in this class. The homework that I assign is like it's the middle of the problems that you should be able to do in this class. I mean, the problems that I assign for homework, you have to do these to have any understanding in this class and to be able to do the take-home test. The take-home test, my take-home test that I give you, are notorious for you're not going to be able to Google it. You're not going to be able to do any research on it and find someone else's problem that's just like that and do it. They are designed so that you have to understand the material. Okay? So like an example of a problem that I'm going to give you on a take-home test would be something like find the equation of the plane that is tangent to the spheres that share common, that have as centers points that lie on a line that is parallel to this. So it's all these concepts put together. And so that you have to understand each thing in order to piece the whole problem together. So, you know, you can't flip through your book and be like, yeah, that problem on the take-home test is just like number 15. It's not going to be there. But you have to do these to even have that chance of understanding what you're doing. With me? So I will push you to understand. Here's what you should do. This is page, don't be scared or intimidated. It's a challenge, okay? It's Calculus 3. It's supposed to be challenging, isn't it? Page 541 actually is where it starts. Problems 3, number 7, number 8, number 10, 11, 13, 15, 18, 19, 21 through 27 odd. The way I write odd is a little odd, so that's the way I write odd. My O's and D's don't really distinguish well from each other, but you do those problems and you'll be at least at a point where when you get the mini test, you'll have good ground to stand on at least. Also, I won't, like the problem in the homework, I'm not going to give you an example of every problem that you're going to do for homework. So it might be, there might be some part of this where you have to make the connection. For example, number 7. I know not everyone has a book. It says, number 7, I'll kind of write it down up here to get you started. It says, find the length of the sides of a triangle that have these 3 points. So it says P is 3, -2, -3. That means the point P has the x, y, and z coordinates of 3, -2, 3. The point Q is 7, 0, 1. And the point R is 1, 2, 1. It says find the lengths of the sides of that triangle. So imagine in three-dimensional space, right, in 3D, you have 3 points, right? It wants you to find the lengths of the sides. Could you do that? How? How would you find the length of, we'll call this L1. If this is P, and this is Q, and this is R, let's just say. What's the length of L1? How would you compute it? It's the distance formula, right? It's the distance formula applied to P and Q. Now, you don't need to have a drawing of this, okay? You don't need to break out your graph paper and try and draw and plot these points. That's not the important part. It's can you just get the result here. Now, if you want to draw, go ahead. I'm not going to hold you back, but that's basically what we have. It's in 3D somewhere. So I could find L1 by finding the distance between P and Q. And then I could find the next one by Q and R, the distance formula. And then I could find R and P distance formula again, right? No big deal. Is that all right? Plug and chug. Next thing. Is it a right triangle? Is it an isosceles triangle? How would you, what's that? Okay, once you know all the sides, then how could you determine if it was a right triangle? What if it's not something special that you know, though? Exactly. You can check for right triangles because they have to satisfy the Pythagorean identity, don't they? So if you get three sides, you take the two smaller sides, a squared plus b squared needs to equal c squared in order for it to be right. And then isosceles, well, you know, do you remember what isosceles is? So I mean, this is an example of this is a homework problem where I would have never shown you this problem, but I would have expected you to be able to extrapolate this from just what I gave you today. Does that make sense? That's the expectation. Another one, I give you a point. Number 8 says, here's a point. Find the distance from this point to the xy plane, to the yz plane, to the xz plane, to the x-axis, to the y-axis. So it's something like, here's a point in 3D. I don't know where it is, just some point. I want to know the distance from that point to the ground, the xy plane. What's the distance from that point to the yz plane? What's the distance to the xz plane? And then, what's the distance from that shortest distance from that point to the x-axis? Or, you know, the y-axis comes out the back here. What's the distance to the y-axis back there? I didn't give you an example of that. Can you figure that out? All right, so you'll have to think about these a little bit. That's the homework assignment. See how you do. Let's talk about 10-2. We still have 30 minutes. Again, I apologize about the way this is printed. You start on the very back, and the staple's in the top right. It's all messed up. I think you have to have like several PhDs to like run the copier the right way. I think they design it just to cause you headaches. Cause me headaches, at least. We ready? Vectors. I know a lot of you have taken some physics classes and you're familiar with vectors, and that's a good thing. We are going to explore in Cal 3 vectors in the definition of vectors as a physicist would see it. There's a more general definition of vectors. If anyone took linear algebra? Nah. No one's taking linear algebra? Okay, you can talk about a vector as being a list of even functions. Take a list of functions that could be a vector, and it could create vector spaces. We are going to stick to the old-fashioned arrow vector from physics, and the thing that makes most sense to us, right? That's where we are, all right? But I wanted you to know, any math majors, vectors are even more general than what we talk about here. Okay, vectors are objects that have two main properties. Every vector has a magnitude. That means it has a length, or what we call its norm. So it's something that has length. Now, it does not have to be an arrow sitting there in space. So this visual thing that you have a vector doesn't necessarily have to be that way. And here it will be, but keep in mind, this is all it takes to be a vector. Objects that have magnitude and have direction. Okay, a way that it points. So this marker is an example of a vector, something that has length, and then I can point it into a direction. As before, we have vectors in two-dimensional space and three-dimensional space. So in this little demo here, it's so cute. You can grab the ends and move it around. Isn't that great? That's a vector. Now I've labeled the vector V with an arrow over it, like this. Anytime you see V with an arrow, or it's actually like a half arrow, it's like we cut the bottom of that arrow off. Okay, that's how we represent vectors. Most textbooks will represent a vector with a bolded letter instead of an arrow, because it's easier to bold on a word processor than it is to do that. But if you're writing by hand, it's easier to do that than it is to bold, right? So it changes. Anytime you see a bolded variable, it represents a vector. So what we have here, do I talk about its tail and its tip? Okay, the tip here is the pointed part. The tail is the back end, right? So tail and tip. In three-dimensional space, you can also have a vector. Now this one, I left it static. It's just sitting there in 3D. You can move this around. You can kind of see, where it is. But same thing. It has a length and it has a direction. What's a little more challenging in 3D is the direction. It's like, what is it relative to? Like here with this vector, you could talk about that direction, right, as almost being like the angle here. But in 3D, what are you relative to? It's a little more challenging, right? Like, where do you orient your angle? Do y'all see what I'm saying? We'll get to it. All right, so this is what I was talking about. Any vector, we do it with this notation or in bold. This is called a displacement vector. We have the terminal point, which is the tip. We have the initial point, which is the tail. Now, two vectors are said to be equivalent or equal if they have the same magnitude and same direction. The position does not matter. So in two-dimensional space, the black and the blue vectors here are equivalent. They're the same. Even though they are in different places, the fact that they have the same length and the same direction does not matter. So I can move the black one around. Those are still equivalent. Still equivalent. Doesn't matter where I move the black one. The vectors are equivalent. So vectors are good because we use them for, like, if you want to describe the force of me pulling this chair across the room, right? I'm applying a force and the angle that I'm pulling is here. Then you could represent the force with the direction, and then how hard I'm pulling is the magnitude. And so it doesn't matter if I'm pulling here in the room or if I'm over here, I'm still applying that same vector force to this. So the vector's moving, but it's not changing. Does that make sense? Or I could go and I could move my arm almost vertical like this and try and pull like that, and now my vector's changed. Or I can go straight, So vectors are nice because we use them for forces and they can move around and still be the same. Okay, now to create a vector, you can create vectors by just having 2 points. Points and vectors aren't the same thing, right? So a vector is created by having 2 points. So determining a vector from 2 points in R2, in two-dimensional space, we say let A equal, what's x1, y1? What is that geometrically? It's a point in two-dimensional space, right? An x-coordinate and y-coordinate. Let B be a separate point, x2, y2. Then the vector from A to B is x2 minus x1, comma y2 minus y1, with these little things around it instead of parentheses. What are those called? Angle brackets. It says it up there, doesn't it? Right? So now what we're looking at is this. If someone writes this down, right, in R2, if they write down 2, 3, that is a point in 2, 3. If they write down angle bracket 2, 3, is no longer a point. It is now a vector. Understand? So all you do is subtract the coordinates, x2 minus x1, y2 minus y1. That's the vector that goes from A to B. If you want to go the other direction, from B to A, look at the way we notate it. It's important here. A to B was that with the little arrow on it. B to A is B first, then A, and then the arrow. And that's the opposite. It's the x1 minus the x2, and then the y1 minus y2. So I have an example here. Let me show the vector from A to B. So I can move my points around. This is actually computing the vector for me. So as you move your point A and B around here, it's computing it. Right? From A to B. And then the other way changes the direction of the arrow. What stays the same, though? If you have 2 points, the length will be the same, right? It's just the direction is different. You've got to get that direction right, though, in these problems, because it makes a difference. Questions on that? Determining a vector from points in R3. So the extension now is into R3. Instead of having x1, y1, x2, y2, we have x1, y1, z1, x2, y2, z2. And as you might suspect, the only difference is that our vector with the angle brackets is going to have 3 numbers instead of 2. And the formulas are pretty much the same, right? Subtract, if you want to go from A to B, subtract the second coordinate from, subtract the first from the second. If you want to go from B to A, you go subtract the second from the first. These are all formulas. So there you go. Go for it. I'll give you like a minute to see if you can get those real quick. Just raise your hand, just like kind of give me a sign when you're done. That way I can, yeah. Okay. All right, everyone should be done by now. Let's see, are you getting the vector -8, 13, 4 for the angle, the vector that goes from A to B? Okay. And then B to A, I won't work it, but what is it? 8, -13, -4. Okay. It's just the signs changed. That should always happen. They should just be off by a sign. All right, we're moving along. That was just a quick little exercise. There's something called the zero vector. The zero vector is the vector, and it depends on what space you're in. If you're in two-dimensional space or three-dimensional space, it's a 0 with an arrow over it, or a bolded 0. I kind of did them both at the same time there. But in R2, it's the vector, angled bracket 0, 0. And in R3, it's the vector, angled bracket 0, 0, 0. That vector, does it have a length? Zero, right? It has a length of 0. So it's like, imagine this is a vector and just shrink it down to where it has no length. So it has no length, 0 length. I mean, it has a length. It's 0, though. So it's not, I'm not saying, there's a difference between saying 0 and not having length. Well, we haven't talked about how to find the length of a vector yet, but the 0 vector is a vector that has length 0. All right, now, whenever we use this notation, this angled bracket, we wind up having, some vector, and then angle bracket, some number here and some other number. Well, those are numbers, we'll call them V1 and V2. Instead of like X1, X2, or X1, Y1, or something like that, we just call it V1, V2. These are not called coordinates. Like in a point, these are the coordinates of the point, right? The coordinates, X and Y coordinate. With the vector, we call them components of the vector. So if you have a vector in R2, the components are V1, V2. If you have a vector in R3, the components are V1, V2, V3. It's just a language thing here, all right? So we understand definitions here. If you want to, you could look at the V1 as being the X component, because it tells you, how far to move along the X. And then the V2 is like the Y, it's your up and down, and Z is the V3. But we say component, not coordinate. Now, we talk about the vector addition, or what's called the Parallelogram Law. When we add two vectors together, whether or not be in R2 or R3, we take the tail of one vector and paste it to the tip of the other. So if I have two vectors here, let's say this is vector 1, this is vector 2, or we could call this V and we call this W, doesn't matter. If I want to add two vectors together, because I can move them around anywhere I want, what I do is I take, let's say, the tip of this one and paste it to the tail of this one like this. And what we get as a result is something that goes from here to here. So imagine connecting now this tail to this tip, and that creates a new vector, and that's called the resultant vector. But I have it here so you can see it. Tip to tail. Yep. So right now, I'm not adding these together, right? What I need to do is move the U over until it touches the tip to the tail. And once I do that, boom, I create this new vector that starts at the tail here on U, goes up to this tip of U and tail of V, and then comes back over down here, so that U plus V is really just going from the tip, the tail of U to the tip of V once they're pasted together. So this black vector is the result of adding those two vectors. Did y'all see that? Sure? Now, I don't know if I have the parallelogram thing here. No, I don't. I'm going to have to do this on the board over here. Or, I'll do it on my thing. Okay, if I take a vector, I'll do it in red, like this. I call this, let's say, U. And I paste to it some other vector v, like that. The resultant, u plus v, goes from the tail of u to the tip of v, like this. That would be u plus v. All right, that would be u plus v. But what if instead I had taken that black vector, instead of doing the tip of u to the tail of v, I did the tip of v to the tail of u. So the tip of v to the tail of u. So move that black vector. So take that black vector and slide it over and bring it down like this. Imagine bringing it over like this and then moving it down until where it touched down here like this. So just kind of slide it. Remember, vectors can be moved around, right? And now when you look at the result, you start here, you move across, you go up like this, and your resultant vector is the one that goes from here to here. That's also u plus v. And notice that these two are the same vectors, right? Same direction, same magnitude. And if you do this, you create a parallelogram. And that's called the Parallelogram Law. It just shows that vector addition, no matter how you do it, it draws a parallelogram, but your results are always the same. Now, the next one is an exercise that I don't think that I'm going to be able to do here easily. Let me see how this works. What would v plus u be here? So if I took v plus u, all I'd have to do is take the black one here, attach its tail to the tip of v, so it would move maybe up and over like that, something like that, and the result would be a vector going from here to here. And I would draw that on there. And then you do the same thing on the other. Now, I don't want to do that, but I would encourage you to try and, on your own, draw that yourself. Be able to, paste vectors together. Question? Now, that's geometrically how we add vectors. The way we add vectors algebraically is pretty simple. All you do, if you have two vectors, u and v, in two-dimensional space, if you have two vectors, u and v, if you want to add them, all you do is take the u1, add it to the v1, take the u2, add it to the v2. So you're just adding the corresponding components together, and that creates your new vector. If you subtract two vectors, then you subtract the components. But remember with subtraction, the order is important, isn't it? If I say u minus v, then I've got to go u1 minus v1, then I've got to do u2 minus v2. And everything just translates down into R3 the same way. Add them all up or subtract. How are we doing here? Let me see how much further we have. I'm not trying to get through this as fast as I can. I'm just trying to see where we are. Components. All right, we can keep going. All right, so we know how to add two vectors together. We haven't done any examples, but it's pretty easy. You just add the components, we're done. Scalar multiplication is something a little different. What we want to do is first understand I am saying scalar multiplication. I am not saying take two vectors and multiply them together. I'm saying take a vector and scale it. That means multiply it times a number. Right now, we don't know how to multiply vectors. We will at the end of next class. We'll have two operations, dot product and cross product. That's the way you multiply vectors. But right now, this is called scalar multiplication. So it says, given any vector v and a scalar c. So scalar means a what? A real number, right? a real number. Given a vector, someone gives me a vector and a scalar, then multiplying that scalar times the vector changes the shape of the vector. If the absolute value of C is bigger than 1, it stretches the vector out. If the absolute value of C is between 0 and 1, it shrinks the vector. So it changes its length. When you scale it, it changes its length. And if C is a negative number, it actually changes its direction. It flips it over and points it the opposite way. Further, if V is equal to V1, V2, then C times V is, what is this? What does this mean? What do you do with that C? You just multiply it to each component. That's all it is. It's almost like distribution, but it's really not. So here we go. I start this out with, there's a vector V, right? It's red and black. If I take 2 times V, it should do what? Double its length. So now you can kind of see, here's V, here's 2V is the red one. So I've stretched it out. Twice its length. If I do 0.5V, it will do half of it. And if I do negative 0.5V, it will do half of it pointed the opposite direction. And then negative 1, what would negative 1 do? Opposite direction, same length. And then negative 2, opposite direction, twice as long. And what does 0 do? Well, it makes my computer not know what to do. That's just a weakness in my coding, but, you know. So that's the idea of scalar. I think you can click this and drag it. Yeah, you can drag it around. You can change your initial vector. All right, let's talk a little bit about parallel, perpendicular. 2 vectors are said to be parallel, and this is the first time for a lot of you that parallels actually means something different than what you've always thought it was. Parallel with vectors means this: they are scalar multiples of one another. Okay, that's all it means. For 2 vectors to be parallel, they have to be scalar multiples of one another. Note, they could be pointed in opposite directions. So if I have this vector right here, I need to get used to not going to the board and just writing on this. If I had, let's say the vector V is 4, negative 5, and I have the vector U is negative 4/3, 5/3. Are these parallel vectors? How can you tell they're parallel vectors? Yeah, if I take negative 1/3 and scale V by that, so that means I'm going to almost like distribute that negative 1/3 through. I get U, don't I? So U is a scalar multiple of V. Therefore, they are parallel. They do point in opposite directions, though. Yes. Yes. Yep. Yep. Okay. I know we're getting close on time here. Magnitude and length. I'm trying to find a good place to stop. Yeah, this might be it. Let's stop there. The magnitude and length is where we'll stop. Homework from here. This won't be the complete assignment, but page 549, just to get you kind of warmed up with the vectors. Number 2 is interesting. Number 3. Maybe number 7. I think we're kind of, that's about it. 7. Yeah, we'll just stop there. My expectation is that whenever I give homework, it's done by the next time you come to class. I will never check your homework. This is grown-up math, right? But I expect you to have done it by the next class. The bonus was to basically derive the distance formula for 2 points in R3. So you have the formula in the notes. Just show me where it comes from. Okay, everyone. See you. You're not turning in homework. Not for a grade. That's right. But I might come in and give you a quiz where I say, let me see your homework. I've done that before, so it's not out of the realm of possibility here.